we're in the back of a rental house. Me and my roommates at Arizona State University. We had welders, saws, grinders. Next to the dryer, where there's a welder, and it was nuts. But there's a fab shop in the back of a rental house, which is not the plan, but yeah, life was really easy back then because in the early 2000s, people were building turbo cars like crazy. Nobody knew what they were doing. They were just
Welcome to the HPO Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Geoff Raicer from Full Race in the United States. Full Race is a company that's been on my radar probably since about the time I started my old tuning shop, and at the time they were really well renowned for building some of the world's best, highest quality fabricated turbo manifolds and turbo kits. They're probably best known for their turbo manifolds for the Mitsubishi, the Nissan and the Honda market, but they covered a wider range than just that. I'd also say that Geoff and Full Race were instrumental in the popularity of the Borg Warner EFR range of turbochargers. Despite all of that and the success that they've seen, these days you're not going to find a single fabricated exhaust manifold on Full Race's website. They've had a massive, complete 180-degree turn in their business model, now focusing almost solely on turbo kits for the 3.5-litre Ford Ecoboost. On face value, this doesn't make a lot of sense, but we thought it was time to get Geoff onto the podcast, dig into his business, his background, and find out why his business has seen such a massive change in direction. Before we jump into our chat, for those who are new to the Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build performance engines, how to tune EFI, how to construct wiring harnesses. We also cover topics on fabrication, 3D modeling and CAD, race driver education, and data logging, just to name a few. You can find all of our courses at hpacademy.com/courses. All of these courses are delivered in high-definition video modules that you can watch from anywhere in the world, provided you've got an internet connection. This means you can learn from the comfort of your own place and you can learn at your own pace. All of our courses also come with a 60-day, no questions asked, money-back guarantee. So if you purchase them for any reason at all, decide it wasn't quite what you expected, no problem, let us know. We'll give you a full refund. And for podcast listeners, you can also use the coupon code podcast75. That will get you $75 off the purchase of your very first HPA course. We'll put the coupon code in the show notes to make it nice and easy for you to find. Lastly, if you like free stuff, then I've got a great deal for you. We are constantly partnering with some of the biggest names in the aftermarket performance industry to give away some great prizes. You can always find our latest prize at hpacademy.com/giveaway. It might be an aftermarket ECU or dash. It could be some engine components or engine building tools, or just about anything in between. They are great prizes and we will ship them free of charge to your door if you're the winner. There's no tricks here, no purchase required to get your name into the draw. All right, enough with our introduction. Let's get into our interview now. All right, welcome to the podcast, Geoff. Thanks for joining us today. As we always do, let's rewind a little bit and learn about your background and specifically how you started forming an interest in cars.
Yeah, thanks a lot for having me here today. I'm excited. So I formed an interest when I was 13 years old, 1993, and my dad had a totally stock Toyota Supra. And his buddy was like, hey, you could get this thing from HKS called a boost controller. And so that was it. He was like, don't tell your mom, right? And then I felt the before and after. I was like, oh, I want to do that for a living. That seems like a good idea. So I went to a engineering geek high school called High Tech High. This was in New Jersey, and it ended up being like one of the top high schools for engineering in the United States. Just out of dumb luck, I ended up there. When we were juniors and seniors in high school, I was working at an engineering firm on Tuesdays and Thursdays. So Monday, Wednesday, Friday, you'd go to school. Tuesday, Thursday, you would intern at an engineering firm. So by the time I graduated high school, I could do some CAD drawings and I understood CNC machining. But at the same time, I had this 1993 Toyota Supra in the back of my head. And then I started on the school bus. We'd drive past this little muffler shop that had, this is 1996, 97. There was a Honda Civic with this giant intercooler sticking out of it. And there was a Supra there. There was a Honda Prelude with an intercooler, and I had never seen anything like it. So once I got my license the next year, I started going there and bothering these guys. And they taught me basics of MIG welding, how to put a turbo on a Honda. And I also watched them break crack manifolds, break turbos. And so, now I'm going to engineering school, have my own B series Honda that's turbocharged and the manifolds cracking. And I'm just trying to support my own hobby and my friends. So I'm in engineering school and started hanging out at this other shop called MaxRev. This is in Arizona at this point, and made my first turbo manifold. So I put pictures of it online, and like overnight, we had people coming in from, I think, orders from Japan, Australia,
Wow.
France, Germany. And I was a 20-year-old kid.
That must have almost been a bit daunting, surely, sort of getting that much interest overnight.
Yeah, it was wild. I think it was just kind of hitting the right place at the right time, and I did everything wrong. So I hired all the wrong people. I had all the wrong processes. We were making the wrong products at the wrong prices with the wrong cost basis. And, running a business is real different from having a hobby that you're super passionate about. So
couldn't agree more.
Yeah, as an engineer, I'm like, wow, this is great. I really like this. And for a bunch of years, I graduated engineering school. And for a bunch of years, we kind of just had a lot of fun. Things kind of changed around 2008, 2009. I think the global recession was in full swing at that point. I had also started working with Borg Warner in earnest at that point. So it was kind of a weird time for our company. We had gone from like, oh, everything's great to, suddenly things are tough.
I think that's probably a bit of a sign of the economic times for every industry around that 2008, 2009. Before we carry on, though, you've just kind of spanned probably 10 or 15 years in the space of 3 sentences, and there's a bunch of stuff I want to dive into in a bit more detail. Back when you said you had that Turbo B series and the manifold was falling to pieces, what was the state of play back then? Because I kind of remember those times myself. That probably coincided with about when I started getting interested in cars turbocharging. And that was really problematic back then. Aftermarket exhaust manifolds, cast, all fabricated, they had a shit reliability record. So what was the problem with the products that were mainstream at the time, and how did you go about trying to fix them?
Yeah, so products that were mainstream at the time were very inconsistent. They were typically made in China, so that was kind of a thin wall stainless steel, probably not back purged TIG weld, or they're cast iron, which generally was also made in China. And so there's a few one-off fabricators who would make things here or there, but at that time there weren't guys who were known as turbo manifold builders or fabricators.
The industry didn't exist back then.
Right? And then turbos, you had like a couple companies who made turbos. There was Turbonetics, Garrett, Precision was like the little baby making Garrett-ish things, and Borg Warner was barely doing anything. So I think that was just kind of the early days. Borg Warner got into it with the S300, S400. Garrett was really leading the way with their GT series from like the late 90s on. And their ball bearing GT's turbos really did stand the test of time for the most part. I think over time, they were probably one of the more influential turbos.
Yeah, I would agree.
So really, tie-out wastegate was a big game changer. I think at the time, your wastegate options were limited to like HKS or, I don't know, cutting some old Audi thing off, out of a junkyard. Right. But Tayal came out with these beautifully like elegant CNC machined with cast valve bodies. And then they introduced the V-band. So I think in those early days, V-bands weren't even a thing. And
No, they really weren't. How much of a game changer, though, in general, like jumping a little bit out of term, how much of a game changer in general has the switch to V-bands been for not only the wastegates, but also for turbochargers? And I've lost count of how many times a fastener on a 4-bolt turbo flange, a T3 flange, would sort of work loose, or the same on the wastegate, and then you have problems with those. It's a pretty sort of noxious environment to try and keep fasteners tight, correct? I mean, people sort of naively think, oh, well, I'll put Loctite on it. But of course, heat destroys Loctite, so that doesn't work.
Yeah, well, really, a lot of people make the mistake of not using a high-temp anti-seize. And I really believe a high-temp anti-seize is the best thing. If you want to keep your fasteners tight and have them able to be removed in the future, high-temp anti-seize, a nickel base, is a fantastic thing to do. And I don't know why people don't, but on V-bands, I'll smear it on any bolt, fastener, bearing housing, turbine housing interface, or anything that's threaded that gets hot. I'd like to put anti-seize on it.
Yeah, 100%. And again, I've probably lost count of the number of fasteners that I've ended up breaking or snapping. They sort of start galling up the threads as you start removing them, and you feel that start to happen. You're like, oh yeah, that 30-minute job's just turned into a 3-hour job. Here we go.
Yeah.
Okay, so coming back to the manifolds, you sort of talked about the options that were available, the materials they're made of. And I mean, you've mentioned China there, probably in a negative sort of stance, and I totally get that. I mean, I kind of developed my business around the time we were seeing cheap knockoff competing products out of China. And on face value, I still remember we were an HKS pro dealer, so we always had HKS product on the shelf, and we had whatever the current generation of HKS wastegate was. And the New Zealand distributor also managed to get hold of this Chinese knockoff. And three of us stood at the counter and compared both the packaging and the wastegate itself. And it took us about half an hour to actually find a couple of subtle little differences. The copy was that good. I mean, it didn't work worth a damn, but it looked the part. So I think like that and Chinese knockoff turbochargers really tainted the whole reputation of the Chinese market. I just want to point out, like, there are some quality products coming out of China.
Oh, absolutely. I mean, at that time, the Chinese turbo
Yes,
manifold
correct.
was really bad. There was a few companies that would produce a product that would just crack instantly, and so that was definitely like a negative at that time.
Yeah, I think what they did manage to do is iterate quite quickly and fix some of those problems. But I mean, yeah, again, not all of it's junk. Definitely not all of it's great.
Oh, 100%.
Yeah, so you've got a fairly good understanding at this point of engineering principles. I'm guessing with this comes along an understanding of material properties, and one of the biggest problems we have with a turbo system is the heat and the heat cycling. So what were your what was your direction to move forward and fix some of these reliability problems?
Well, at that time, 304 stainless was considered a higher end material. Very few people used a 321 or anything more exotic than that. And it was also tough to get mandrel bends. There's burned stainless, and they were expensive, and their bends would pretty much crack. And so people would make log manifolds out of steam pipe. And so we just started buying steam pipe in various alloys. And then I was luckily located in Arizona, where there's a huge pipe company. And I ended up meeting their supplier randomly, and we started experimenting with different alloys and different variants of stainless steel and different thicknesses. And what we found is Schedule 40 is really thick and really heavy. And if you don't want this thing to break, you better make it out of Schedule 40. The vibration that a 4-cylinder internal combustion engine sees, and combined with the heat, the temperature, it's pretty violent. So V8, V6 engines, they're different. They don't shake like a 4-cylinder shakes. So these motors are really hard on turbo manifolds. And what might work fine for a multi-piston engine, 6-8 cylinder, is not going to work fine on a 4. So certain engines really, like Miata motors, Volkswagen Audi 1.8T engines, Honda S2000 engines, some of these engines just eat turbo manifolds. And if you don't overbuild it, it's going to crack. So I feel like that's probably an area that really forced our hand in saying, all right, Schedule 10, Schedule 40, you're going to gain about 3.5 pounds right there. And more significantly, you actually lose a little bit on the ID of the tube. So that kind of became what is available? So you had 1.25" Schedule 10 or 1.25" Schedule 40. And then you have 1.5" Schedule 10, 1.5" Schedule 40. And what's very tricky is 1.25" is more like 1.4 inch. 1.5" is more like 1.6 inch. And so it's not exact, it's called nominal diameter. But what you really want to think about is, what do we want the inner diameter to be? And then what do you want the wall thickness to be? So I think more often than not, people in our space tend to think that you want huge runners and big giant horsepower, and that doesn't really pay dividends on a turbo engine.
I think that's always been the way with everything. Turbo manifolds, turbo sizing, wastegates, head porting, cams, bigger is obviously better. And I think that's still a perception that exists today. And it couldn't be further from the truth. I think it's all about optimizing every part of that package for the particular application. And go big, and all you're going to do is create a lot of lag, a late boost threshold, and a car that, particularly if it's a daily driver, is going to be dog shit on the street.
Yeah. And so we pretty much started experimenting with that. So I started with big runners, and I found that, hey, you can make some top end horsepower, but it is doggy on the street. And then we started sizing runners differently, and hey, you can find a whole lot of free gains in the mid range with virtually no loss on the top end if you go a little smaller. And then we started, experimenting with that. So yeah, long story short, we built a few manifolds, built some for some friends, and everybody seemed to really like them. And we had some orders from around the world come in, and things changed. Then we started building them for 2JZs and for SR20s and 3S GTEs, whatever, RB26s.
Wherever the popularity was.
Yeah, then we adapted the RB26 manifold so that the same head flange would also fit a 25 and a 20, and that the SR20 would also fit the VE head. So for guys who want to swap, so you start just evolving and trying to keep up with whatever the current state of the art is,
Okay. I just want to carry on down the path of the materials just for a moment. You talked about the 304 stainless thin wall and then the Schedule 40. I mean, a lot of people listening probably haven't seen Schedule 40 pipe. Can you give us a sense of what the wall thickness is for conventional thin wall 304 versus the Schedule 40?
Yeah, so a typical 304 might be 1.5 millimeters thick. A Schedule 40 is about 3.5 millimeters thick.
Okay, so massive difference in wall thickness. And is that where the strength and the reliability comes from, or is it also around the alloy of the material itself that you're using?
Well, there's a lot of factors here, right? So Full Race was actually able to customize our alloy. We're adding a little bit of nickel, a little sulfur, a little molybdenum. But beyond that, the way that the tube is formed, so this thick wall pipe is actually cast or forged in an elbow shape. And that means there's no residual stresses in that tube from the forming. Whereas if you take a straight tube and you mandrel bend it, you have all these built up stresses going through the material. And yeah, that's a beautiful way to build a header, but it is a higher stress way. And so in the case of a 4-cylinder engine, if you're a real motorsport race team building high-end endurance racing stuff, you got to use a high-end material. And a Schedule 40 pipe is not that. A Schedule 40 pipe is for a guy with an Evo or, one of these Japanese cars trying to turbocharge it well, cost effectively. But if you're looking to build a motorsports grade header, you're talking $3,000+ in just raw material.
So then we're sort of moving to what, the likes of 321 or Inconel?
Yeah, exactly. A 620. So Inconel is a brand name for a high nickel super alloy. 625. There's other variants. 6XN, I believe, is probably the more common. So talk about Chinese. They make a beautiful Inconel knockoff called 6XN, and it's about 1/4 the price of an Inconel tube, and it has virtually all the same characteristics. So Hastelloy, which I think is the owner of the Inconel brand, is probably pretty displeased about that.
Okay, I can only imagine. Yeah, I do remember, I think it might have been when I was developing our Evo drag car, and at the time, I was sort of looking around for materials, not that I was going to fabricate it, but materials for the turbo exhaust manifold. And you look at the upper echelons of professional motorsport with turbocharged engines, and 321 was the product of material of choice. And I looked into that at the time. I don't think anyone in New Zealand had 321, was unheard of. Burn Stainless, which you mentioned earlier, I think they were one of the few places you could source it. But I mean, the cost was just out the gate, and it was just a hard no for us.
So it's alloyed with titanium. I don't know if you know that, but that is actually part of the reason.
Yes, yeah, I did know that. Yeah,
yeah, it has a high titanium percentage, and it's not the worst to work with. It's not the best, but it's expensive, especially because of its demand for aviation applications. So most aviation headers are required to be built from 321.
Yeah, it makes sense. Sort of, it's hard to pull over to the side of the sky if you end up cracking an exhaust manifold in your Cessna or whatever it might be. Okay, just with respect to the materials as well, I've always believed that the material and the manufacturing sort of process that you use for designing and building a header is one part of gaining reliability. But the part that's really easy to overlook as well, particularly when you start looking at these thin walls, say let's call it 321 stainless, you've got that manifold that's going to be glowing bright red hot when it's being beat on really hard, and that sort of tends to change the material properties. It becomes softer, malleable, and then on top of that you've got this big heavy turbocharger, perhaps a wastegate and a front pipe hanging off that manifold. And then to add insult to injury, we're bouncing the car up and down as we're going over bumps on a racetrack. That to me is kind of a recipe for disaster. Am I on track with that? And if so, how do you combat the weight of that turbocharger being supported by the manifold?
So it is glowing red hot, it's expanding, and it's moving and bouncing. There's two trains of thought here. One is that you kind of want the system to be able to float and expand and grow and move around on its own. The other train of thought is you want to constrain that. So you want that turbo bolted to the block, and you want the header to be able to just do whatever the header's going to do. But if you're going to bolt the turbo to the block, you're going to find that it's going to stress the manifold to cylinder head studs. So where that manifold bolts to the head, if that turbo is fastened, that load is going somewhere. There's just no way around it. So I think that in racing applications where you have to save every gram, if you're going to go make a super thin wall, thin flange, pocketed CNC, everything beautiful about the header, then yeah, bolt that turbo up and don't let it move. But if you're an application like a big heavy truck or an Evo that's going to go drive a whole bunch on the street, and I'll just go thick wall or a cast manifold in that instance, whatever, just something that's super beefy and doesn't really care what's attached to it. It can, it can handle a lot more than that.
It's got the mechanical strength to support the weight of the turbocharger.
Yeah, because it allows the whole system to move, and it really does. It doesn't stress the system and try to bind it up.
Yeah, okay. I kind of went down the path with a lot of my own stuff where we would build a turbo support. And so I guess maybe this comes somewhere in between the two options you're talking about there. It wasn't a rigid support because we used rose joints or rod ends on each end of that support bracket. Maybe it'd go from the turbine housing or core down to the engine mount or something like that.
Yeah, the oil drain or something.
Yeah, and it would allow, it would support the turbocharger vertically to a degree, but it would allow some movement. Of course, the argument then is, the turbocharger can only move through the radius of that link. I get that, but we're trying to find a compromise here for a pretty shitty situation. So is that in your eyes viable?
Yeah, absolutely. Anything you can do to reduce stress in the system is a positive. You just don't really want to introduce new stresses whenever possible. So yeah, you're right. Everything has a compromise, but in general, if you can have a Heim jointed, rose jointed scenario where it's able to have some degrees of freedom, some ability to expand and contract, then that's going to be a positive.
The other thing I always try to do as well is support, let's say we've got a longitudinal insulation, north-south engine, and you could end up essentially almost having half of the exhaust system also supported off the back of the turbocharger. So again, to try and sort of overcome some of that, I would always try and build in a mount for that exhaust front pipe prior to a flexi joint, so that again we've got some support for that whole system. I feel like we're probably getting a little bit down in the weeds with this, so we'll try and get back on track. Now, I filled in some of those gaps that I think you kind of just glossed over there, but it also sounded to me from what you were explaining that you pretty much jumped straight in the deep end and founded Full Race without, other than you mentioned you were sort of doing your work experience job with your engineering firm. Did you have any prior jobs, or was that the case? You jumped straight in and started Full Race?
Yeah, I've had some jobs. I used to work at a bike shop when I was growing up in high school. I worked at 3 engineering firms. I worked at a CNC shop. I worked at Max Rev, which was a racing / turbo shop. So they were really into 2JZs. And then around that time is when I started making my own stuff. And it wasn't that I jumped into Full Race. I think Full Race jumped into me. It kind of just took on a life of its own. And, we're in the back of a rental house. Me and my roommates at Arizona State University, we had welders, saws, grinders. Next to the dryer, there's a welder. And it was wild. We turned this. It was nuts, but there was a fab shop in the back of a rental house, which was not the plan, but one thing led to another, and I got a smaller shop, then a medium shop, then a few years later a bigger shop. Yeah, life was really easy back then because in the early 2000s, people were building turbo cars like crazy. Nobody knew what they were doing. They were just trying to buy turbos, from anybody who had them. And if you could make a turbo manifold, then you were in a very small pool of people who actually understood this stuff. So.
In those early days, how many staff did you have?
Full Race never was bigger. Actually, back then we had between 20 and 30 guys, and it was wild. It was so inefficient. We had so many orders coming in for high labor, high touch products. So when you're building a turbo manifold, And if you get 20 orders for a turbo manifold, it's like, oh man, we got to go build 20 of these things.
Is it time consuming, right?
Oh, it's crazy labor hours. And so that was the mistake I kind of made from a business perspective. I chased my passion, which was this art of building these beautiful turbo manifolds. And the reality is, you kind of have to be a little bit insane to do this because it is hours. And there are some guys who can knock it out. A lot of my former employees are now building their own turbo manifolds and they still love it, you know? So I feel like if that's your vibe, then you can definitely spend hours doing it.
So, yeah, I totally agree. I mean, I do not claim to be a fabricator. I don't think I'm very good at it. I don't enjoy it. But in the past, where I've kind of had the need, I've built maybe half a dozen, maybe 10 of my own exhaust manifolds myself and for customers back in the day. And it's a pain in the ass. It's a very time-consuming process. Admittedly, all of those ones that I did were one-offs. Clearly, you're making production manifolds off a jig, slightly different deal, but doesn't make it necessarily a heap less time consuming. So you're sort of getting into this situation where you're trading hours for dollars, in this case, your employee on the end of a TIG welder, putting these manifolds together, and you've got a finished product that you can sell.
Yeah, I mean, what you just said makes a lot of sense. Like for a guy like you, or really a lot of your listeners, building your own exhaust manifold, turbo manifold, is something that can't be replaced because if you have a specific turbo and a specific setup that you want to execute, it's highly likely that you're not going to get anybody else to do it as well as you want it to be done because this is a really technical thing and it's tough to get stuff that's off the shelf that really meets your needs. So yeah, for somebody who's a HP Academy regular guy and understands the intricacies, I think that it makes a lot of sense to make your own turbo manifold. So when you're doing it for a business, though, that's different because you're trying to make one design that fits a whole lot of people's needs, and that's a very challenging thing to do in this environment.
I guess the other issue is sort of stock or inventory and trying to look into the crystal ball and see where the demand's going to be so that when orders come in, you can ship product without hanging your customers out to dry for weeks or months. You know, how much of a challenge is that?
Oh yeah, it was impossible, absolutely impossible to get that right. You always had the wrong stuff in stock because if it was hot, it was out of stock, and if it wasn't hot, it was stuck on the shelf for 2 years. It was a constant battle to try and chase. And you know, the reality is if you don't have it, then the guy's going to go somewhere else and find something else that is available. So telling someone the 2 months or whatever, 6 weeks, 4 weeks, whatever it may be, yeah, it doesn't really fly in this day and age.
Now, another technology I wanted to talk about back in that time, I know that you were also using robotic welding for your manifolds. And I can only imagine what that might look like. What drove you towards going down that path? Was this for speed or strength or aesthetics or tick all of those boxes above?
I'll answer that by saying if anybody listening wants a robotic welder, we've got a couple we'll give you a sweet deal on because we're not using them anymore. But the reality was it created the perfect weld. They were so beautiful. They were so perfect. We didn't have a single one crack in like 20 years, probably 19 years. So we had a couple different machines. So machine number one came from a company called Liberty Dimetrics. They were in South Carolina. This was a pretty expensive machine at the time. It's old school and it's still going strong. It is wild. We had a few variants. There's a few issues with it over the years where we get a new motherboard replaced here or there. So we ended up buying like 3 of them and it became like this crazy reliable old school machine that would just robot weld all day, every day. And so eventually we ended up upgrading to a Miller machine. Their company is called Jetline Automation. And so they basically made a slightly more modern, easy to repair, whatever, easy to get parts for version of this old Liberty Dimetric machine. But the whole idea is that we're able to weld Schedule 40 pipe in a fusion, and we're not actually adding filler rod to it. And so that's actually desirable because adding filler rod is a foreign material. If you have a fully inert environment, you can fuse two pieces of steam pipe together as if it's just steam pipe. And you can do it in such a beautiful way that it creates and it's just an aesthetic difference, but it creates a really beautiful rainbow and the beads are super tight. So it's unlike most hand welds you've ever seen. And not to say it's impossible to do it by hand. I can't do it by hand. I don't know too many people that can. It takes a positioner and a pretty special setup to be able to pull that off without a robot. So it really did save some time. It allowed an average person to become one of the top turbo manifold TIG welders in the world just because you put this thing in and We called it PhD. It was push here dummy. You line it up and you push the button and off it goes. And it was like this perfect thing. So
am I right in assuming this still, because you're dealing with stainless, which is a reactive material, you're still back purging with this robotic welder?
Yeah. You always want to back purge when you weld stainless steel.
All right. So let's catch up to speed now. You started talking about the change in the economy around the sort of 2008 GFC and post 2008. You've really now had, from what I can see, almost a full 180-degree change of direction with Full Race. So yeah, bring us up to speed on what that looks like.
So back then, Borg Warner was working with us in the early days, and economy starts falling apart, and they came to us and they said, listen, we know nobody's selling anything right now, so you can either curl up into the fetal position and just wait for this to be over, or we could get busy, get some work done, and see what comes of it. So I said, yeah, let's do it. And that was really the start of the EFR program. And the EFR program kind of brought us enough on Borg Warner's radar as being guys who you could depend on to do some crazy projects, that they said, hey, we're working with Ford on this project. Would you be interested in building some prototypes? So we said, yeah, let's hear it. And so Ford comes to us and they basically said, every engine that was a V8 is about to be a V6 twin turbo. Every V6 is about to be a 4-cylinder turbo, and every 4-cylinder is about to be a 3-cylinder turbo. And we want you guys to make some prototypes for us. So we're not going to pay you, but we are going to give you free engines, and we're going to give you like crazy in-depth engineering data. So are you in or not? And for me, I was like, that sucks. They're not going to pay us, but this is the coolest opportunity I've ever heard.
It's a hard sell.
Yeah. And I mean, we did some projects with Toyota, with Honda, some other OEMs, but it wasn't like this, where they're going to send you a prototype engine 3 years before the rest of the world could see it. And so I was like, yeah, we're in. Like, let's do this. And so they sent us the first V6 Ecoboost engines. I still have it in my shop. And we built some crazy attempts at turbo systems, just blind, no idea what we were doing, because half the stuff was missing. The whole vehicle wasn't even created yet. We didn't know what the build envelope looked like. So they ended up taking the stuff back, digitizing it, putting it in their software, and giving us unbelievable CFD data. So they were able to identify like every exhaust molecule and fuel molecule and the combustion process, like millisecond by millisecond, every crank angle. Like, it was unbelievable what we pulled out of this project. And really what that did was introduced Full Race to Ford in a first-class fashion. I believe very strongly that what that project led to is what we now know as the 2.3-liter EcoBoost engines. There's a few engines like that, Volkswagen's EA888, for example, but the Mustang EcoBoost twin scroll, also Focus RS EcoBoost twin scroll, had 3 distinct ports: cylinder 1, cylinder 2, 3, and then cylinder 4. And then what Full Race had done at that time is we modeled a twin scroll versus a single scroll system. So we actually built 2 completely separate turbo manifolds kits for one engine. So the original EcoBoost 4-cylinder engine was sold in Europe on the Ford Mondeo. It was a 2-liter engine called the Classic, and it had like just traditional 4-port head. So we took that head. It looked like our Evo 10. It was basically our Evo 10 manifold. So it was an Evo 10 twin scroll and an Evo 10 single scroll. And we sent it to Ford, and they tested it, and they're like, oh my God, this is crazy. The twin scroll exhibits much higher peak, and the single scroll exhibits much higher average exhaust pressure. And that was really insightful. So in the end, time to torque is the metric that OEs often use to identify how responsive a turbocharged engine may be or how laggy it may be. And the time to torque of a twin scroll engine was just unbelievable in how much faster that higher peak.
So I just want to dive in here and just stop you for a second, because there's a lot of confusion around some of these metrics that we use to kind of define turbo performance. The term lag is thrown around, and I think a lot of people misunderstand what lag actually is. So if we look at it from a perspective of, first of all, I define sort of boost threshold. So an RPM point above which we have enough exhaust gas energy to actually produce the boost pressure we want. So, within reason at 1500 RPM, we're unlikely to be able to produce, let's say, 18 psi of boost pressure. There's just simply not enough exhaust gas energy, unless we size the turbo so small that beyond 2000 RPM, it's a waste of time. So that's boost threshold, which I think is what a lot of people refer to as lag. Once we're above that boost threshold, so let's say we're 5.5, 6,000 RPM, so plenty of exhaust gas energy there, we're off the throttle, and then we jump straight back on the throttle. The time it takes for the turbo to get up to full boost, that's kind of what I reference it as lag, which it sounds very much like your time to torque metric. Am I right there?
So that would be a transient recovery, right? So on-off throttle, that's a transient. So overall boost threshold is where it's going to come back in. I perceive lag to be just a general all-encompassing term of what happens when a turbocharger is too big for an engine. It's not a specific, and we could totally dive into the nitty-gritty if that's where this conversation goes. I'm fine with it.
Well, I think probably it's one of those things that lag you're not going to necessarily notice or measure on a dyno. So you're going to have a power and a torque number, which is great. But you can also have two turbochargers, particularly when we start looking at some of the more advanced and lighter materials for turbine wheels, or more modern designs in CFD for turbine and compressor wheels, where we might be able to make the same peak power and torque numbers, but the lag or that transient response is cut in half perhaps for the more modern turbocharger. Again, that's not necessarily going to show up on a dyno sheet, but the driving experience for that turbocharger is completely different. Would you agree with that?
Yeah, like if you're behind the wheel and you want power, there is nothing worse than going wide open and not having the power that you want, right? It's an incredible sensation to want power, hit the throttle, and have all the power in the world. And it's an incredibly deflating, disappointing sensation to have the opposite of that happen.
Definitely. All right, so in terms of twin scroll versus single scroll, I'd like to think that most people listening probably have heard the terms and hopefully understand them, but just so we're not leaving people out to dry, could you give us a quick high-level overview of twin scroll versus single scroll and why the twin scroll improved that time to torque that you mentioned?
Twin scroll is pairing cylinders, complementary cylinders as opposed to interfering cylinders, so that when one cylinder is exhausting and the exhaust gas is flying out, the other cylinder that you're pairing it with has its exhaust valves fully closed. And that does not allow the exhaust gas pulse to go back into the cylinder and contaminate the charge. Furthermore, it does not lose the kinetic pulse energy because it's bleeding back. It's just a maximum of pulse is hitting the turbine wheel, is impacting the turbine wheel. Now, there is a downside to that. And because you've physically divided them, you've introduced a dividing wall, which does increase friction. And so this is going to have a more negative impact in a drag racing application that's super high RPM based, which really any sort of wall friction is going to negatively impact a very high engine speed RPM. And in that instance, you're going to want to try and probably go with like a V-band setup. But if it's time attack, drift, road race, or street use, especially on a small displacement 4-cylinder engine, twin scroll really works remarkably well. And going further, twin turbo on a V6 or a V8 engine, that's really the same thing as twin scroll. Obviously, you don't have a common shaft, but you have a divorced cylinder bank separating the exhaust event.
Yeah, okay, makes sense. When you're looking at a V6 or a V8 engine and single turbocharger, it's probably getting a little off track, but just seeing as you mention it, a single turbo versus twins, obviously from a packaging standpoint, if you want to run one big single, the manifold path is just inherently, it's got to be long to get to that central turbocharger wherever you happen to mount it, versus twins, essentially you can have them nicely closely packaged up to the cylinder head. Your exhaust manifold runners are shorter. How much of a difference does that make to the boost response, boost threshold, etc.?
It's really hard to quantify that. I think in general, oversized headers are not good, but a single turbo V8 rips. It's like if you got the displacement, who cares, right? And
you can't argue it works.
yeah, I mean, when you've got displacement on your side, you can get away with all sorts of stuff that shouldn't work, and it works just fine. And I feel like that's the big differentiation is there are no one size fits all rules. This guy's got that and that guy's got that turbo. Everybody runs some unique setup, and you can usually make something work. And so ultimately, it's like, what are you building? Because the way I look at it is it costs about the same amount of money, time, effort, whatever, to build any car, right? That sure, there's Lambos and some GTRs that might be more expensive, but for the most part, whether it's a truck or a car or a V8 or a Ford, it's almost the same amount of shit. So, it kind of just depends on what are you trying to do and figuring out how you're going to achieve your goals.
Talking about there's, sort of a million different combinations that all within reason get the job done and work. I mean, the other part of that is in the enthusiast market, no one really has the money to A/B test, two different setups. You commit to your path, you build the combination, and hopefully you're happy with it, and that's that. You don't most people aren't going to then in a year's time, reconfigure the entire system and try, we're a single turbo, now we'll go twin turbo. How does that work? So it's probably rare that happens. That's more at a OE level or the development that perhaps you're doing. Another part that I just wanted to dive into a little bit deeper, this has interested me. You mentioned your relationship with Borg Warner, who are a manufacturer of OE turbos. I've had this conversation with one of the engineers at Garrett at SEMA. This would have been back pre-COVID, I reckon, maybe 2019. And the conversation came out of the Garrett engineer more than Borg Warner, but I'm going to assume the same goes. And basically he said to me that the Garrett turbos, and we as car enthusiasts know Garrett as a performance turbocharger. The reality, however, is that they're a supplier to OEs. And I think at the time, don't quote me on the specific numbers, he said their performance aftermarket turbochargers were something like 5% of their total turbo production. Which to me then begs the question, I'm going to assume, the reason I raised Borg Warner, I'm going to assume it's probably something similar with them. It begs the question, why? You're producing turbochargers for OE manufacturers, and I can assume they put in their order for, let's say, 10,000 turbos a month for this model of car. The turbos ship. The phone never rings. They don't get technical inquiries or emails. They just go about their business. Whereas as soon as you sell a turbocharger on the performance aftermarket, you've got every man and his dog trying to fit these turbochargers. The level of understanding and knowledge is very variable. And I can imagine they're just opening themselves up to just technical queries and failures and warranty claims and all the rest. So the question in that is, why do these OE manufacturers still focus on the performance aftermarket to a degree?
So I think the answer depends on who we're talking about. I think in the case of Garrett, they are very much steeped in racing history. Garrett, I went to the 24 Hours Le Mans with them, which was an incredible experience. And, seeing how serious Garrett still is. I went to a Formula One race with them in France years ago. It was incredible. And these guys they're serious about racing. That is their passion. They use it as a marketing mechanism. And I think that the universal racing turbo thing is short of saying it's becoming less relevant. But I mean, I look at Borg Warner for that matter. The EFR program was born out of IndyCar. Had IndyCar not signed a contract with Borg Warner for the EFR program, that probably would have never happened. And, there are other race teams and sanctioning bodies that use EFRs, but, ultimately that was IndyCar. And so to answer Borg Warner's why, well, IndyCar was why. For Garrett, I think it's a marketing expense, 24 Hours Le Mans, Formula One. MHI, totally different deal. They're just trying to make a couple bolt-on turbos. They make an awesome plug-and-play bolt-on turbo for the Civic Type R. Our customers love it. So every turbo manufacturer is in the aftermarket for very different reasons. And so why, it's going to depend on who or what they're trying to get out of it, I think, ultimately, if that answers your question.
Is there also sort of an element of, the technology developed in the racing or performance turbochargers kind of filtering down over time, and what they learn there getting applied to OE turbos, therefore advancing the whole turbocharger market?
I think to an extent, yes. Generally, the technology is changing so quickly year to year. The aerodynamics understanding and designs are changing so rapidly that you'll see the aftermarket universal turbos are lagging. And when one of these companies introduces a universal turbo, they're generally not going to touch it for like 5-6 years, and then they'll update it. But right now, every 1, 2, 3 years, there's like a whole new era of aerodynamics coming in. So some of these smaller companies that are more agile are creating more aggressive compressor sides. But, and this is a big but, it's hard to beat the Garretts and the Borg Warners at the turbine sides. Obviously some people are innovating there, and I think what Tyal's doing is really interesting, especially when it comes to like plug and play. Tyal's turbine wheel is remarkable in a hybrid setting where you're trying to do a plug and play upgrade. It's incredible in that environment.
What makes it so special?
Okay, so the Tyal turbine wheel, I think they call it like a splitter blade wheel. So it's like one full size blade, one clipped blade, one full size blade, one clipped blade. And my limited understanding of this is that it allows the exhaust housing to flow more as if it were a larger exhaust housing, right? Obviously, you're not able to change the size of the exhaust housing very easily. So I think if you are constrained in exhaust housing size and we want to get more flow out of it, I think Tyal's solution is an elegant way to do that.
So this is almost a modern take on the old school technique. I mean, back in the day before we had access to any of these performance aftermarket turbos, the obvious hybrid modification was to fit a slightly larger compressor wheel to your existing turbocharger. So by definition, that then allowed the potential for more compressor flow. But at that point, we haven't dealt with anything on the turbine side. So the technique there was to back cut or clip the turbine wheel, basically sort of machining. It's hard to sort of describe without a picture, but sort of machining an angle on the extruser, opening it up a little bit. I guess that was the crude, dirty way of what you're talking about here with.
So that actually lose some turbine efficiency. And so talking about turbine efficiency for a second. So the turbine efficiency, the way it works is right around a 1.0 AR, you're going to have your maximum turbine efficiency. If you're under 1.0 AR, you're going to have your balanced turbine efficiency to flow. If you're above 1.0 AR, you'll get more flow for less efficiency. And as you go under 1.0, you get less flow for more efficiency. So this is a battle, right? Now, most people consider something above a 1.0 to be big. It doesn't necessarily mean that. It's just really, it's all relative, right? And if it's divided, you want it to be huge. If it's divided, you could be on a 1.4 or 1.5 even, and not necessarily have a negative. So again, it all depends entirely on what the application is and what the objective is. So if it's a Garrett G30, G35, generally people are going to run that undivided, but there is a divided housing for it. And as we were talking about earlier, it's just a complex way that you're going to have to make your own exhaust manifold if you really want to try and integrate a divided header. Whereas
it's going to be a lot of work.
Yeah, you can get a V-band manifold just off the shelf. So that's the predominant configuration, is a single scroll V-band. Anybody can go buy a V-band manifold and slap that thing on. It's a lot easier.
Yeah. No, that makes sense. I just wanted to take a moment out of our interview with Geoff and talk about a course that's going to be perfect for those of you who want to start designing your own components, such as exhaust manifolds and turbo kit components. And that is our 3D modeling and CAD for Motorsport course, normally valued at $199 US. You can use the coupon code RACE50, that's RACE50, to get $50 off the price of this course. This course will take you from zero previous knowledge on CAD and 3D modeling software and teach you essentially everything you need to know. You'll learn about the basics of CAD, what CAD is, the different types of CAD software that are available, pros and cons of each, and the required hardware. You'll learn about the fundamentals of design, which is really important when you are designing components, making sure essentially that they are fit for purpose from an engineering standpoint and are going to be strong and safe. You'll then learn about the basics of solid modeling, such as datums, 2D and 3D sketching. You'll learn about extrudes and holes, revolves, sweeps, piping, lofts, and more. We'll then move into sheet metal modeling basics, which is a really powerful aspect of modern CAD software, converting your model to sheet metal. We'll talk about bends, flanges, flat patterns, and bend back. You also learn about assemblies and analysis. You'll also learn about post-processing, such as drawing fundamentals and setup, part drawing views, dimensions and tolerances, drawing notes, and other specifications. We'll also cover advanced CAD topics topics such as surface modeling, simulation and FEA, generative design, and automated modeling. We'll cover in brief 3D scanning and printing, and then we move into the 5-step HPA CAD design process. Now, this is a 5-step process that you can apply regardless whether you're designing a full tube chassis, an engine block, or a turbo manifold. The reason we do this is by breaking the entire process down into 5 individual steps. Each of those steps is relatively quick and easy to complete, and in no time you've got your finished model. And this is going to make sure that you haven't overlooked any critical steps that could waste time, money, or end up adversely affecting your finished product. The course also includes a library of worked examples, which is an informal walkthrough of that 5-step process where you can see it being put to work, making a real-world part. Remember, that course normally $199. You can use that coupon code RACE50 to get $50 off, making it just $149. Even using that coupon code, you are still protected by our 60-day no questions asked money back guarantee. So if you purchase and for any reason at all decide it's not what you expected or not right for you, let us know. We'll give you a full refund of the purchase price. Now let's get back to our interview with Geoff. All right, filled in a few more gaps there. So let's get back onto this sort of Ford and Borg Warner development path. You know, we left off where you were sort of talking about the split pulse, divided versus single entry. So where did we go to from here?
Yeah, so we did this. Ford was really happy with the work. They determined that this divided split pulse design works really well in 4-cylinder. And then the 6-cylinder twin turbo engine was what later became the 3.5 liter EcoBoost in the F-150. So we were done with the project. There's actually a cool article about it on our site. I don't know how long it's been since it's updated, but you can see the study with some of the CFD data. It's on our site, fullrace.com. And what happened over time was that project was done, and Ford's like, all right, thanks. And everybody at Full Race was like, that's it? Like,
now what?
All that? Yeah, exactly. So I got a lead and I sent an email to Ford marketing and I said, hey, listen, we just did this crazy project with everybody. We're really excited about it. It seems like it's over. Is there any way we could continue? They're like, yeah, submit a proposal. Tell us what you want to do exactly. So I sent them a whole proposal and like blew my mind. They said, yeah, we'll give you a pickup truck. You guys can go do this. So they sent us an F-150. The catch was that we had to bring it to SEMA. We're like, okay. And so Borg Warner put it in their booth and it was pretty cool. We put a single turbo on it, which actually worked very poorly. So that was a perfect example of single turbo not working well on a V6. We ended up going to twins, which worked really well. I still have the truck running with the exact kit that I put on, the twins kit from like 12 years ago. It's my daily beater out here. So that thing's still going strong. But that really kind of changed the way that I perceived what performance turbocharging was going to look like in the future. And so I moved to Arizona when I was 19 years old, and I loved video games like Ivan Stewart's 4x4. And, the idea of this sick Toyota pre-runner, long travel with like AR, I love that stuff, right? And so even though I was into cars and racing, I always kind of had an eye towards that. So when I was in college and when I was starting Full Race Up, there was a shop out in Phoenix called Geyser Brothers. And I used to go hang out at Geyser Brothers, and I started building a Toyota truck. These guys had the craziest trophy trucks. And I don't know if anybody listening knows who Geyser Brothers is, but their level of fabrication is just art. And now they're doing billet portal 4x4 long travel. Like, you don't want to be against Geyser in the Baja. They're just not the dudes you're trying to beat. So I was really lucky. I got to hang out there, sweep their floors here and there, and pick their brains. And it really got me going thinking about trucks. So then I joined this forum called the Race-Desert Forum. And this was like the early days of pre-runners and chase trucks. And I started getting to about the same time I'm doing this full race and turbo fabrication, all that. So when this Ford opportunity came up, and then they said they're going to give us an F-150. And at this time, they're also releasing the Raptor with this big, giant 6.2 liter V8. I'm like, this is just so cool. I got to get into this. So we got this first truck, twin turboed it, made 500 horsepower. And we figured out that you could put an intercooler in one of these trucks and it'll allow you to put a winch on them. And a lot of people with big trucks want a winch for recovery and off-road. So we started selling these. And then it turns out, you want a pre-runner bumper, you're definitely going to need this intercooler. So the intercooler started gaining popularity. And I think at that time, people weren't really doing that. People weren't modifying EcoBoost F-150s and putting intercoolers in bigger turbos. So it was very low adoption. We were still focused on Evos and Subarus and Hondas and whatever else, Toyotas, Nissans.
And I guess at this point as well, you're fairly early to the market with these products.
Way early. People didn't even know that you could get a F-150 with turbos in it, and so Ford's not even sure how to talk about it. But then, a year later, they basically said, we're going to spend more on marketing for this word EcoBoost than all other campaigns in history of Ford combined. And I was like, whoa, that's crazy. And so we're like, yeah, let's just try to make EcoBoost. So it was like crickets, we sold 2 intercoolers this month. And then one day we sold like 8 intercoolers. And then we sold a turbo. And then, things kind of evolved. And then one day Ford says, well, we're going to bring out this thing called the Raptor in a couple of years. It's going to have an updated EcoBoost engine that has a stronger bottom end, port and direct injection, bigger turbos, and all this cool stuff. And I'm like, oh, this is just the craziest thing ever. So that was really kind of the beginning of the end for our obsession with Japanese imports, because simultaneously, like, you couldn't get a good car from Japan, right? Like,
it's changed, hasn't it? Yeah.
So Ford started producing these insane twin turbo V6 engines by the millions, and we couldn't get anything cool from Japan. So my team is kind of looking around going, what are we doing?
I think I read a statistic, and I can't remember if the number I'm about to say is correct, but it was something mind-blowing that per year Ford are selling something like 900,000 of these trucks. Again, don't quote me on it. Could be off the mark, but the reality is essentially that the numbers that they're shipping are just so massively skewed compared to the rest of the cars that you're supporting.
I feel like it's like every 33 seconds or 38 seconds, another one comes off it's insane, right?
Just coming back a step to where you said that you put in this proposal and Ford gave you a truck and they had to go to SEMA. I've always been interested about the relationship OEs have with the aftermarket. I mean, there was a rumor, which I have absolutely no idea how much truth there was in it, with the JDM models that 6 months prior to a new Nissan 200SX or whatever it might be coming out and being released, they would ship one to Greddy and they'd ship one to HKS so that they could start developing products, so that when the car launched, there was already aftermarket support. Sounds like Ford kind of almost were going down that route as well. Where my question is here is, how do they weigh up? I mean, I know you're not Ford, but if you've got some insight, how do they weigh up this, making the car appealing to the aftermarket who want to modify it, with also thinking about how they're going to maintain warranty support for these trucks that are now getting heavily modified beyond what Ford ever expected?
Yeah, I think warranty is always a concern, and Ford probably doesn't want to deal with that at all. If someone's going to go void the warranty and then try to claim warranty, I feel like that's probably the last thing they want to deal with. So, in general, they're excited that we're pushing the limits of what's possible. And, if there's racing or, engine swaps, stuff like that. But people who are expecting to maintain a warranty with a 4S kit are probably fooling themselves.
I think most people would also understand that that's not going to fly. If you're going to modify your pickup truck like that, you're kind of on your own if you put a rod out the side of the block. But I guess obviously for Ford, it must be that the making this new F-150 appealing to the enthusiast market is important to them.
Yeah, especially at that time when everybody just wanted a V8, and they're going to try and introduce small displacement turbo engines, so they needed all the help they could get. And I think just positive excitement about turbocharging was cool at that time. Now, that tune has changed. We had a great relationship with Ford until about 2020, when I believe Ford pulled out of SEMA and said, hey guys, it's been fun, but we don't need you anymore, right? We're not doing SEMA. We're not doing these projects. And so I'm really grateful that we were able to get in at the right time and on the ground level, get the engines and kind of the engineering support that we did, because now I believe that I probably understand these 3.5 liter V6 engines better than most. There are definitely some weak points on them that can be addressed, but these are serious trucks. They're expensive trucks. They're a lot of fun. They're all-wheel drive with a whole bunch of wheel travel. So I don't know if you guys, if your listeners are mostly outside of North America, I assume many are, but if you ever get a chance to really hoon a Raptor, even just in two-wheel drive locked rear diff, it is just so much fun,
Yeah. In terms of those weak points that you just mentioned, I'm guessing this sort of comes a little bit outside of the products you're actually developing, but sort of what are the weaknesses? What tends to let go and what needs to be addressed?
So first of all, there's 3 generations of these engines. So there's Gen 1, Gen 2, Gen 3. Gen 1 was 2011 to 2016, and that's a DI only engine based off of the old Mazda Duratec V6, also known as the Ford Cyclone engine. So it's a 3.5 liter V6 twin turbo, and really it's a pretty robust motor. It's got a decent crank, decent rods. The cam gears, also known as the phasers, are probably the most obvious point of contention, but in general, it's a good motor. It just has an excessively long timing chain that tends to wear over time. So yeah, Gen 1s are okay. Their issue is they just can't make a lot of power. And the reason is they're limited by fuel system.
As soon as you're stuck with direct injection only, it's difficult. There's not a huge amount of additional headroom generally in factory direct injection fuel systems. And you can't sort of go to Injector Dynamics or whoever and just buy a set of off the shelf 50% larger injectors.
Yeah, so you upgrade the pump. A few companies use a Stanadyne, that's the OEM Chevy pump for like a big Chevy LT. They remachine it and stick it on the Gen 1s, and it makes a bit more power, so you can make 500 and change, and that's fine for stock bottom end. That's where I'm at. I'm like 550 on ours. It's been going for 12 years strong on pump gas, and it goes forever. It's fine. But if you want to go a little bit faster, that's when Gen 2 starts to make sense. And so in 2017, Ford did 2 big things. One is they released the 10R80, which is their 10-speed transmission. And then they released the Gen 2 engine, which was dual port and direct injection. And that was a game changer because you could upgrade the DI, you could upgrade the port, and now the sky's the limit in how much horsepower you can make. So Gen 2 EcoBoost, overall, great platform, awesome for making power, but there's a few weaknesses. So weakness number 1 is the crank pulley. It is not well damped. Weakness number 2 is the oil pump. It goes from a standard operating mode to low oil pressure, low parasitic drag mode. So say you're idling and you're sitting there and engine's warmed up, oil's up to temp. It goes from like 60 PSI to 25 PSI of oil pressure. I do not consider that a positive. And if you look at what this gear is, what a normal beefy oil pump gear should look like. Well, this is like, it looks like a power steering or like an ATF kind of gear with the veins sticking out. It's just not a great oil pump. So resolving that, definitely something. The phasers and the timing assembly, timing chain guides, those are all like probably the most well-known weak points. And the solution is very simply, you use a Gen 3 timing phaser guide, tensioner, chain, blah, blah, blah. So the Gen 3 engine, they got it all right in the Gen 3s.
Yeah, okay. Makes sense. They work through these bugs over time.
Yeah, exactly. They fixed it. So the final major issues that didn't get resolved with the Gen 3. So there's coolant lines there's an O-ring that tends to leak at around higher 80, 90,000 miles. So Full Race kind of replaces that entire assembly. The other aspect is the turbocharger. So 17 to 20 is when Borg Warner's Gen 2 turbos were electronically actuated. And I'm a huge fan of electric wastegates. I don't know if you have a lot of time messing with them, but being able to command wastegate position is really incredible. I want the wastegate closed. You don't have to trick a spring and a diaphragm with a boost signal and bleed valves or anything. It's just wastegate closed. It closes. Wastegate open. It opens.
Yeah, it makes a lot of sense.
Yeah. I feel like that was really a big turning point. So the injection combined with the wastegate control. The event that really poured the gasoline on the fire for the Raptor and EcoBoost world was when Garrett released the Power Max turbo. So that was a bolt-on, plug-and-play, like 500 plus setup. You could do 700 on ethanol. But to be able to make that kind of power in an all-wheel drive truck with a lot of travel is so much fun. And once you experience that on a bunch, like in dirt, big tires, whatever, even on asphalt, it kind of changed my perspective to saying, you know what, racetracks are cool, but just going out in the dirt and having fun. My kid's in the back seat, I'm scaring him, and it's just so much fun. And it kind of brought me back to what I felt like when I got back into cars originally, was just like overwhelming smiles, and I think that's kind of the change. So I've gotten older. I'm 44 now, and I think when I was younger, I was really into beating the clock and being the fastest dude around a track, and now I'm just trying to have as much fun as I can.
Yeah, that makes a lot of sense. I mean, that's what cars are supposed to be about, just having fun, smiles per gallon.
Exactly.
In terms of these Garrett PowerMax turbos, so let's sort of get a comparison. Yeah, if you've got a stock set of turbos on your Gen 2 or Gen 3, what sort of power level can you get out of one of those on pump gas safely before you sort of out a turbocharger?
You might get to 500. You're spinning the thing crazy. And there's some dudes who'll put it on ethanol and maybe get high 500s, but you're overspeeding the stock turbos so hard and you're choking that motor through the housings. You know how that all works out. So,
Yeah, okay. All right, so we go to the PowerMax turbos. Again, pump gas and ethanol. What sort of power can we get out of this?
yeah, so pump gas 550, 580 without breaking a sweat. Ethanol 650 to 700, a little strung out. That's a lot of power.
And at this point, are we sort of getting to the mechanical strength limitations and things like connecting rods and pistons?
Exactly. So yeah, oil pump, connecting rods, pistons, crank, all that stuff's kind of in play. Generally, pistons are okay-ish, rods are okay-ish. Yeah, you could throw one out. I'd be more concerned about the oil pump. So the solution that I'm working on, it's not fully vetted yet, but I believe we can run. I test fitted on a block actually just the other day. We can run a Boundary makes an awesome billet oil pump for the Gen 1s. So it looks like that'll be able to be adapted to the Gen 2 and the Gen 3s to solve the oil pump issue. But the Gen 3 gets the strongest crank of any EcoBoost engine. So the solution, if you're building a Gen 1 or a Gen 2, just get one of the Gen 3 cranks. They're super cost effective, and I haven't seen a single one break yet.
Yeah, okay. I mean, I think with crankshaft technology, I don't know for sure about the EcoBoost, but I'm going to wager a bet here that it's a forging from the factory anyway. And I mean, I think that's really been the norm for just about any performance engine I've dealt with almost in my lifetime. It's a long time since anyone's really been messing around with cast crankshafts, which are a potential disaster. And a good quality forged OE crankshaft can be really strong.
Well, we have seen some crankshaft failures on the Gen 2s, and I actually believe it's largely comes down to a harmonics issue with the OEM crank pulley. If you look at what Ford did on the Gen 3 crank pulley, it's actually really interesting. It's this huge fat inertia ring, and they moved the AC pulley forwards like 2 inches to accommodate this giant damper. So obviously someone at Ford is paying attention to vibrations.
Sure. All right, so I guess at this point, what's Full Race's sort of development and product lines looking like for the F-150? You mentioned the intercooler. Where I'm going with this is, you're best known for your turbo kits with these fabricated manifolds, which we've already talked about. Now, Garrett are making these PowerMax turbos that are a direct replacement bolt-on factory-style turbo. Why not just buy those and bolt them on?
Oh, you can, and it'll work real well for you. There's definitely nothing wrong with that. But if you want to do things right, you can obviously, instead of the cast iron log manifold that comes on the Raptor, you can use a thoughtfully designed stainless steel full race manifold. And it's, individual runners with a merge collector, and it's a very techy part. Another thing is the bolts that attach, or studs rather, that attach the manifold to the cylinder head. They're one-time use from Ford. It's a mild steel magnetic bolt. Or stud. You don't want anything to do with that. You want to replace that with a multi-use. In our case, it's an Inconel stud. The water lines are kind of failure prone and not the best solution. So I feel like ours is a little bit more elegant, a little bit more reliable. And, in general, there's just a lot of small things that we kind of add value to the system. So yeah, you could throw a set of turbos on it and it will work for you. But you could also replace all the other parts at the same time. And that's really where Full Race comes in. We've been in the game for a while. We understand what it takes to be a turbo supplier. And I also understand that I can't beat Garrett at building these PowerMax turbos. They do a great job. There's electrical actuation and really thoughtful bearing housings. I'd rather do business with Garrett, make them a key trusted supplier partner of ours, and then we can do all the stuff that Garrett can't.
All the support structure around the turbocharger, and you leave that to Garrett.
Yeah, absolutely. There's some things like the downpipe, the way the downpipe attached to these turbos, it's really tricky. And if you use the factory part, it's like 2.0 inch. Ours is 2.6, and ours is a perfect fit to the Garrett. If you're using the factory one, it's like so small, you're probably going to be down at least 60, 80 horsepower just from that one part.
Wow. Okay. Yeah, that's pretty significant. The manifolds that you developed for the Ecoboost, these are stainless, as you mentioned. These are cast though, as opposed to fabricated. So this is quite a change from your previous manifolds. And I'm interested. Is this just a sort of economies of scale? You sort of got to a point where
So we tried to fabricate, like, I don't know for how long, F-150 headers. We tried every which way. I don't know, like, how to even describe it in a podcast, but it wasn't happening. The only way that you can make a header fit in this very tight space constraint, which is also heat sensitive with a plastic valve cover and electronic wastegate actuator right next to it, you can't have runners all over the place. It had to be super compact. And so we have an absolute all-star engineer, Matt, who works for us. Love the guy. And he put the time in, and this was one of his pet projects, created what we call our form-line turbo manifolds. And so this is such a tight space constraint that the runner is actually integral to the head flange. And the design actually required special clearances to be able to have a socket to fit in, because otherwise, and you know how it goes, installing parts that aren't designed to be installed, you're not getting a tool in there. And you got to start the nut we can't do that to our customers, And so we really put a lot of time and effort into creating a comprehensive kit that makes working on these trucks kind of pleasant.
it does really make a difference, because I've been in that situation more times than I care to think about with some aftermarket exhaust manifold, often from well-respected suppliers. And when you actually go to bolt it on, like you say, you just, there's no way you're going to get a socket or even the closed end of a ring spanner onto your manifold nuts. It's just, like, who designed this? Did they actually?
Oh yeah, well, I'm guilty of that, man. We did that for years. And the fact is, if you're welding something, if you're fabricating a manifold, that's going to happen. But if you're building something in CAD and you're 3D printing and you're test fitting and you're going through the process to try and vet all the bugs and the gremlins out before releasing it, that's really where Full Race is today. And so a lot of the stuff that just didn't meet that bar has been discontinued. And I think a lot of people don't understand that when you get to a certain level in the automotive industry, the professionalism and the requirement to produce a part that really stands out, it's not easy. And there's a lot of guys who have a welder and a bandsaw and a grinder in their garage, and they were perceived as a competitor to Full Race. But if you want to be a competitor to Full Race now, you got to be on top of your game, because this stuff is techy. This is some seriously challenging work that we're doing.
Am I right in assuming that another benefit with these cast manifolds is just the ability to produce them in huge numbers quickly? I've already talked about the labor-intensive process of hand fabricating. Assuming that's the case, though, with casting,
So investment casting is a funny term, because it has nothing to do with the actual upfront investment.
No.
But it actually does have everything to do with the actual upfront investment, because the amount of time that you spend in your CAD model and your 3D printing and your test fitting and all of that is going to greatly impact your end result. Because when you go to say, here's my money, I want you to go make the tools, those tools are expensive. And if you made a mistake, you are going to pay. And that is the worst feeling. Retooling is bad. It is really bad. And so the way I look at it is, if you're going to play the game of casting, you have to be able to do a really, really good job up front before the first one gets made. And if you can do that, then you could probably cross over into, this makes sense. But for us, we really want to be specific about what we're going to target.
In that respect, obviously, the technology we've seen just generally that the aftermarket performance industry has access to is dramatically changed over, since the time maybe you are designing and hand fabricating exhaust manifolds for Mitsubishi Evo. I'm talking here about CAD, easy access to CAD, and then more importantly around 3D printing. That technology it really wasn't available at the enthusiast or even semi-professional level back in those days. Could you have produced the same exhaust manifolds without CAD and 3D printing that you've done now? How much of a game changer has that technology been?
So CAD and 3D printing are a double-edged sword, because it really has evolved so much that it made me realize how bad we were in the past. And so I really kind of look at the tools we have available and say, why did we ever do what we did? And I hope we never do that again. And so now, like, my 8-year-old kid is obsessed with 3D printing. Like, we don't buy toys, we 3D print them. And I feel like households everywhere now have access to a 3D printer. So, a few years ago, this was expensive technology that was really difficult to access. And on top of it, a lot of people are using filament printers. I saw you guys did a episode on resin printers. There's laser powder binding printers. There's so many different types of 3D printers that really the sky's the limit. And I feel like we're still in the very early stages of what's possible there.
Yeah, I think Connor is our sort of in-house pro when it comes to 3D modeling and 3D printing, and he's got a course coming out on 3D printing specifically in the not too distant future. But I mean, the sky is really the limit when you've got access to that technology. And as you sort of mentioned, the price has come down so dramatically. An enthusiast level printer, you could probably buy something pretty easily now under $1,000. And I mean, that's still, granted, it's still a fairly substantial investment for a lot of people, but it's no longer sort of in the $10,000-$20,000 vicinity for the enthusiast, just completely unattainable. And the great thing we've got to look forward to is, I guess, at some point, and it's probably still going to be a fair way down the path, we're probably going to see the same drop in price for 3D metal printing, which is still a technology that is incredibly expensive. So you're going to have that next generation of step in technology again.
Yeah, and I'm excited because we've seen huge advances in 3D printing of all types, for production purposes.
Yeah, I think it used to be seen that it was really only any good for prototyping, but now the reality is that there's definitely a case study for production parts being 3D printed. So yeah, absolutely. All right, so obviously at this point, deep in development of these products and kits for the 3.5 Ecoboost. However, it seems from looking at your website, it's sort of been to the detriment of every other product line that I previously knew you for. So again, as I alluded to earlier, a complete 180-degree turnaround in your business direction. I'm interested why not just add to your product line with the Ecoboost components and retain everything that you're already known for?
Yeah, a lot of reasons. One is, we believe if you want to truly be great at something, you have to walk away from the other things that you're okay at. And I believed we were good, but we weren't great at certain things. And so we want to be great with the Ecoboost Raptors. Like, that's our focus. And to walk away from everything else allowed us to have just 100% focus on one thing. And so I actually recently sold my Evo. That was my baby for, 15 years. I had a ton of fun with that car, but maybe it was more than 15 years, actually. Probably 20 years I've had that car. I own, I think, 3 or 4 F-150s right now. It's insane. So I feel like I am the kind of guy who, if I'm going to do something, I have to fully immerse myself in it. Break the truck, rebuild it, take the motor apart, take the turbos out, rewire something, and constantly messing with it and really experiencing what it is to own and modify that vehicle. So for me, everything else became a distraction.
How important do you think it is as a business owner with Full Race to sort of own the vehicles that you're developing parts for? Plenty of companies will buy a truck, develop the parts, and then sell it. The owners maybe got no interest in actually owning that vehicle. How does that change the way you think about the way you develop parts?
This has been a big argument internally with me and my team, because I was along the side with what you just said. Like, I was that guy who just build a vehicle. We did an FRS BRZ kit years ago, bang it out, get rid of it next, then do a whatever and do it again and do it again. And when you don't have that emotional soul attachment to a vehicle, I think it comes off in the product.
You're not trying to make it the very best that it can be.
Yeah, it doesn't have that extra little bit that actually is needed to make something succeed. And while there's certainly some, I guess, poetry there, because the guy who actually really understands it is going to always have that, upper edge kind of. It's going to be tough to take the edge out on someone who really gets it.
Yeah, okay. In terms of what Full Race is today, sort of asked the question earlier, but now what's the size of your team, and
Yeah, we're the smallest we've been in years. I think there's 9 guys at Full Race right now. So yeah, previously when we were building the manifolds, we were anywhere from 17 to 20 plus guys. I think at one point we were just close to 30. And now we're small, we're lean, we're really focused on what we are and are not doing. And ultimately, the biggest project that we're working on right now is this Gen 3 Raptor. We have a kit that's going to come out for the Gen 3 Raptors, and that's a 2021 up. And I don't know if you're familiar with this, but the big change that the 2121's got, so they got a much revised engine, slightly revised transmission, but they went to a 5-link rear suspension, and it has like 15 inches of travel. So when you're mobbing like across the desert with live valve shocks, this is fully electronic. I think it's like 300 times a second adjusting the valving. It's really incredible how high performance a pickup truck can be.
Yeah. In terms of the changes for the parts you're developing for that Gen 3, how dramatically different is that from your perspective to the Gen 2?
It's very similar. In fact, it's striking how similar it is. But there are some differences. So the Gen 2 has a linear wastegate actuator. This is a traditional electronic wastegate like you've seen on the Supra or the BMWs, Civics. And in Gen 3, they went to a rotary wastegate actuator. So instead of just a straight line, it's actually on arc. And this convoluted the compressor housing a bit. It changed the turbine housing. It was really, I love everything they did on the Gen 3 except the turbo. And so what we did was we took our Gen 2 Garrett kit and updated it and made it work on the Gen 3. And so far, it's been absolutely amazing how well it worked. We lucked out on a few things, and it's obvious that Ford is sharing architecture because some of these things shouldn't have worked out as perfectly as they did. But generally, when you're developing a kit, you hit roadblocks and hurdles, and you're trying to solve them in the best way possible, the quickest, easiest, fastest, whatever it may be, way possible. In this instance, we had already solved these hurdles. So now it was kind of like, all right, well, can we do that better? And even though there's a solution there, how can we make that better than what that solution already was? And so we're re-examining everything from the gaskets to the studs to, the oil feed lines and return lines and coolant lines. And this stuff really does matter, especially in a truck that's like 5,000 pounds, 700 horsepower. There's so much energy going on. And if this thing's in the middle of the desert, you can't deal with a coolant line failure, dumping all the coolant line. Like these trucks can't break down. So reliability is like the number one factor for this application.
Yeah, fair. Obviously, you're deep in this Ford world. Are you looking outside of the Ford market for, competing trucks or other vehicles that you may also look to develop? I mean, I guess I see a potential for, you're putting all your eggs in one basket with the F-150. That allows you gives you the advantage. You know it inside and out. You're hyper focused on that one product line. But I guess there's some risk of exposure if something changes in the market.
So to answer your question, you're 100% right. And I was with you. I checked out the new Toyota. It's a 2.4 liter. Then you got the 3.5 liter Toyota. The Chevy, there's a 2.7 liter 4-cylinder twin scroll turbo. Borg Warner makes that turbo. That's pretty cool. Jeep has something. Dodge has a 3-liter inline 6 knockoff of a BMW, right? So there's all these different engines out there. And we just went and bought a 3-liter Ford Ranger Raptor last week. So to your question, yeah, I'm branching out from Ford 3.5 into Ford 3.0, which is different, but it's similar-ish. And so I don't know if you know what the Ranger Raptor is. That thing is pretty sick. They're available out there. Really good platform, incredibly capable Watts Link rear suspension. So I think that's actually the coolest truck out there. In fact, obviously, I just bought one, so it's like, there he goes. I wouldn't have bought it if I didn't like it. Yeah,
it says a lot. Yeah. Okay. So sounds like still Ford through and through. When you are like assessing potential new vehicle for development, what are you kind of measuring its potential success against? Is it the potential market size or popularity in the aftermarket or something else altogether?
All of the above, right? It all varies. But the number one single biggest factor you gotta know ahead of time is, can the ECU be tuned?
Yeah, that's something we haven't actually touched on so far. Obviously, there's no point adding bigger turbos and the potential for 700 horsepower if you can't actually do something to extract that with the ECU tuning.
Yeah, and I've made that mistake before. We've developed parts for platforms, and we're like, oh, oops, that was a big waste of time. So now, if I have confidence that the ECU can be tuned, like 100% confidence, we'll go in. So like the Ranger Raptor, I would have been scared of tuning that, but I know for sure that you can. The answer on that thing is you can't tune a Ranger Raptor. ECU is fully encrypted. So you get an F-150 Raptor ECU, you flash it to the Ranger Raptor program, and then you can tune it. And as stupid as that is the solution.
The great thing is that the aftermarket tuning industry is incredibly creative. And the number of times I've heard of ECUs coming out that these ones are untunable, uncrackable, no one's ever going to be able to deal with this. And 6 months down the track, everyone's tuning it, and you're like, well, that didn't age well, did it? And there is so much demand, and for the companies providing tuning solutions, obviously so much money to be made that they're going to put a lot of engineering sort of resource into finding solutions. I mean, I'm not saying that it'll never happen that we have an untunable OE ECU. I'm sure there are ways that could occur, but so far it's been pretty successful, I think, in the aftermarket.
Yeah, I will say though that Cobb gave up. A few companies have definitely given up on this Bronco / Ranger ECU, and the solution of swapping is definitely in play right now. So if you can tune them without swapping, that's a lot more desirable.
Yeah, and I mean, obviously the low hanging fruit there as well. If it's going to take too much engineering resource to do, option A, well, is option B viable? Yes, maybe in time you'll find. I mean, we have was it a 2018 Chevy Duramax with the turbo V8 diesel? I can't actually remember the engine capacity now, but I mean, back in the day, HP tuners. If you wanted to tune that, you had to send the ECU, in our case, all the way to America. Probably much, much easier if you're already over there for this unlock, and the same with the transmission control module. And it was a massive, massive pain in the ass. And now that same model, you don't need to do that anymore from memory. I could be talking out of turn here. But so, the technology does sort of march on. I mean, that was an expensive process to go through. So that's a barrier to entry for a lot of people who just won't tune the vehicle because it's just too expensive. Break down that barrier, all of a sudden, you've got more customers coming to market. All right, what if we could look into your crystal ball, given that you've been so deep in the world of turbocharging for so long? I mean, it baffles me how much advance we've seen in turbocharging technology probably in the last just 10 years. And sort of, I wish I could almost have my time again with my drag car. We were running a dirty old HKS T51R SPL ball bearing turbocharger, which was essentially a Garrett core anyway. It's a pretty dated turbo by current standards. And I'm sort of thinking to myself, how much further can we go? Are we going to start finding less and less meaningful improvements in this turbo technology, or is this still the sky's the limit?
Yeah, that's a pretty wide open question. I think what you're seeing in the drag race world is absolutely insane. Like the speeds, the power that these guys are making, it's nuts, right? I didn't even think some of this stuff was possible. And if you talk to some of these engineers who were working for major turbo companies a few years ago, they would have said it wasn't possible. But guys are doing it, right? So obviously there's tremendous aerodynamic benefits. And ultimately, when someone's designing a turbocharger, generally you got to have a really good indication of what it's doing. And so, in the case of these small guys doing it, they're using CFD software, which is, I know some of these big turbo companies aren't even having to burst contain stuff because they're able to get the software to simulate such accurate outputs that they're like, oh yeah, that thing is going to contain without actually having to test the burst container on an engine stand. And that's a unbelievable thing that you can achieve that through a computer software simulation.
So I take it from that point, you think it's sort of that advance in CFD that's driven a lot of the improvement we've seen in the turbo technology?
Just analysis in general of CFD and FEA.
I guess back in the day, they came up with a new design for a compressor wheel, and the way to test that was to physically make the compressor wheel and then test the turbo and, benchmark it and see how it performed. Now, all of that can essentially be done in the virtual world before a single part's actually made. Therefore, you can iterate faster and get to the finished product much quicker and cheaper.
Yeah, and so there's some guys are starting to machine the shaft into the blade of the wheel, and you ask an engineer, that's not going to do anything. It's already It's at the centroid, and there's no airflow there. But these guys are making a ton of power. So just because an engineer says it doesn't work, maybe some guy is able to trial by fire, trial and error, get it to work, and just getting more airflow out of this thing. So I am not a PhD aerodynamicist. I have no business designing a blade set, but I've met a few of the guys who do, and they're really smart. You got to be a different kind of breed to be a aero guy, but I respect those guys immensely. I think most people kind of look at whatever Pulsar or someone sticking out as, oh, that's good, but they don't realize what really goes into making a first class, first rate compressor wheel. The new Garrett GX race turbos have a really nice comp wheel for, I think, the drag race class. The Borg Warner EFR Blacks have a really aggressive inducer. The Zona stuff, this guy Tate, he's the aerodynamicist for the Zona turbos. Unbelievable work that these guys are putting out. So in general, I would say that you're going to see the smaller guys release newer products sooner. You'll see really cool stuff from some of the bigger guys. Borg Warner released the SXR series. Those turbos are really good aero, unbelievably durable, great bang for the buck. Just every company kind of has a different ethos and a different angle that they're trying to chase. MHI, they don't make any universal turbos anymore, but they make awesome plug-and-play Evo, plug-and-play Civic Type R, plug-and-play Subaru, whatever turbo. So, ultimately, I think each company has their own thing, and that's what racing's all about, right? Everybody brings their own different take to the table.
Yeah. All right, so a couple more questions that just cropped up while you were talking there. The first of those is, a smaller company, and just because you mentioned them, I'll sort of take Zona Rotor as an example there. Do you see their size as a pro or a con, maybe a feature or a flaw when it comes to competing with the bigger players, let's say Borg Warner or Garrett? Can they be more agile and change direction faster? I'm guessing it's probably safe to say they don't have the financial resources and engineering resources of those big players. So yeah, give us your take on that.
Yeah, agility, it's going to be tough for a big company like a Borg Warner or Garrett to do anything. If they want to do a project, it takes them like a year to just agree that they're going to start the project. You know what I mean? Whereas Zona is like, oh, we're going to go do this. And then they can go do it. And so there's pros and cons to that, because I'm in that situation, right? I'm a small guy, and I can just decide today that I'm going to go do this project. But there's a price to pay, because that means I'm not doing those other projects. And so in the case of Garrett, once the production button gets hit, their factory in wherever, Mexicali, starts pumping that thing out. And then if Borg Warner hits boom, then their factory in Ramos starts pumping that thing out, or Asheville. If Zona wants to do it, they have to take away something to do something. That's just the reality of being a small business. But I will say, their agility and their ability to design a turbo that fits a unique need is unmatched. A case in point, my last project before I said we're going all in on F-150s and all this, our last project was for the new BMW M3 M4. So it's called the S58 engine. And this was a hybrid turbo, so we can't change the turbine housing easily. And we wanted to stick the highest flowing guts in it we could. So I went to Zona and I said, I think your UHF turbine wheel would work really well here. And it did. It worked unbelievably well. We replaced the journal bearing with the Zona billet ball bearing cartridge. And they machined the comp housing to be a 3-inch portage shroud from what used to be like a 2 1/4-inch just standard inlet. It is unbelievable. Those guys are absolute wizards what they were able to do. Like the first time the car went down the track, it set a record. The second time it set some other record. When some other car broke some other stock motor, whatever. Like, the reality is, no Garrett or Borg Warner could have, would have, should have, or ever will do what Zona just did. But for the S58 community, that's a significant thing, because those turbos are phenomenal. So I feel like in general, it's a pro and a con, and Garrett Zona should never try to act like each other. Garrett's going to fail if they try to act Zona. Zona's going to fail if they try to act. You got to know your role, know your lane.
Know your strengths and play to them.
Yeah, that's it.
Yeah. The other question that I wanted to ask as part of that was you sort of mentioned universal turbos and now direct fit or factory style replacement turbos. Do we still have a market as cars get more complicated, turbocharged cars get more complicated? Is there still going to be a market for these universal motorsport style turbochargers, or are we going to see a shift to more and more application specific plug and play turbos, as you've called them?
The shift has already happened. In fact, I believe COVID accelerated that shift. So in the late 20 teens, there was a very clear trend that application specific plug and play stuff was going to be growing for customer demand reasons. But then the EPA came in, especially in the US, and that became, you have to do plug and play, because if it's not, it's whatever, Clean Air Act and cats and whatever else. So as long as you just keep a stock cat in it, you're probably going to be okay. And if it's plug and play, it's probably going to keep a stock cat in it. So then that kind of went down the path of, all right, if we're going to try and make plug and play turbos, how does that work versus if you're going to try and make universal turbos work? And at the same time, there was a inundation of universal turbos. You had this one guy, VS Racing, and then there was Pulsar and all these. So all these companies start making universal turbos, and obviously Precision gets bought by Wabtec, and they're just pumping turbos out. There are so many universal turbos on the market. It's pretty overwhelming.
Saturated market.
Yeah, it's a saturated market, and the market is not growing, right? Because most of these universal turbos are going on older cars. There's not too many new cars that are getting universal turbos installed, that even can get a universal turbo installed on it, right?
Is a bit of that down to kind of there's just no real estate in a modern engine bay to do a conventional fabricated manifold with a...
Yeah, and most of them don't even have manifolds, right? It's integrated.
Yeah, true.
The world has changed.
Yeah, where the turbocharger essentially bolts straight to the cylinder head and the exhaust manifold is integrated in the head. And that's all kind of really about sort of minimizing that flow path, as I sort of understand it.
Right. And you have B58s and S58s, and there's a few cars here and there that'll get fabricated manifolds, but for the most part, it's definitely, Universal is just not growing like it was.
Mm. I guess as well, this makes it simpler for modifying the car. I mean, if you've got a plug and play direct fit turbocharger, even as you say, I mean, you've obviously made your own water lines, oil lines, etc. for the F-150 Ecoboost to fix some other problems. But if those problems didn't exist, literally bolt all your lines up to the new turbocharger and you're off to the races. So yeah, couldn't really get too much easier than that.
Yeah, it takes a 2 or 3 day turbo kit install and turns into a 1 day install, and people like ease of installation.
Yeah, definitely, can't argue with that. All right, Geoff, I think we'll move on here. I want to respect your time, so I think we'll finish up here. And we've got the same 3 questions we ask all of our guests at the end of our podcast. And the first of those is, what's next in the future for you and Full Race? I think probably we've maybe touched on a couple of the new models you've been looking at, but anything else you can give us there to maybe fill out the future a little bit more completely?
Yeah, so I'm pretty much exhausting what you can do with the Gen2 Raptor format. I've got this truck I'm building as maximum as I can build this thing. I've got a Gen3 Raptor project in the works. And I am going to kind of revitalize my old RB26 R14. I don't know why. Just sentimental, nostalgic reasons maybe, But ultimately for the company, Gen3 Raptor is where I think we're headed. That's, to me, kind of the pinnacle of what is possible for the light truck market. So that's my focus.
Yep. From everything you've said, makes perfect sense. Our next question, is there any advice you'd give to a younger version of yourself or to one of our listeners to help reach where you are today in your career faster, or potentially avoid some of the pitfalls you've come across along the way?
Don't give up. If you have a dream, stick with it. Definitely get educated. I think a lot of people kind of use the school of hard knocks to get educated, and it's a lot more painful. It takes a lot more time than if you could actually... MIT has all their courses open sourced. You can learn so much stuff for free on the internet today. So whatever it takes, I really encourage education.
Yeah, I couldn't agree more. It's never been easier to learn. I mean, obviously that's why High Performance Academy exists. I'm going to add to that, though. I'm going to chuck in my unsolicited 2 cents. From listening to your story here, I'd also say don't be afraid to pivot when the market changes. I mean, I could be very wrong, but I imagine that you pre-2008 GFC probably could not have visualized what Full Race has become today. I don't know, I might be speaking out of turn there.
So we really made that pivot in like 2021, 2022. So this is fresh.
Notwithstanding sort of same still goes.
Yeah, there are still days where I miss the old ways, but the reality is I don't regret it. When you see something, you got to go for it. And sometimes they call it killing your darlings. You got to say goodbye to whatever's holding you back, because if you want to get to, they say the only way to add sometimes is to subtract.
Yeah. Yeah, and it's got to be a tough decision to make, such a dramatic pivot in your business model, but clearly it sounds like it's working out for you. So all power to you.
Yeah, appreciate it.
All right, last question for today, Geoff. If people want to follow you and see what you're up to, how are they best to do so? What's your website, social media accounts, etc.?
Yeah, our website, full-race.com. Our social media is at Full Race Motorsports, and our YouTube is at Full Race Turbo. So there's some videos that we did on the YouTube recently. Feel free to check them out. And we're always updating our Instagram pretty regularly.
And as always, we'll put links to those accounts in the show notes to make it easy for people to find. Look, Geoff, a real pleasure catching up and getting an understanding of the direction the business has gone in. Really exciting, particularly what you're doing with the 3.5 EcoBoost. Seems like maybe the sky's the limit. So wish you all the best for the future.
Yeah, thanks a lot for having me, and hopefully you'll get some of those motors down under at some point.
Absolutely.
All right, man. Cheers.
If you enjoyed this episode of Tuned In with Geoff, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Phil from the UK, who has said, great podcast, HPA dispelling the narrative of a lot of aftermarket tuners that you have to be born with their abilities or don't even bother, breaking down complex subjects and introducing new topics with industry guests. Great compliment to their courses and gives me knowledge in areas I wouldn't typically dive into in a full course. Well, thanks for the kind words there, and it's great to hear that you're enjoying the podcast. If you get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.